Hello. Here we'll talk about elementary transformations of rows of matrices interpreted as matrix multiplication. The matrices which will perform these elementary transformations are called elementary matrices. So the story goes like that. We have three types of elementary transformations. And we usually use them on rows to transform a given matrix to a special form called row echelon form, reduced row echelon form. The size of the matrix, of course, doesn't change, but the content does, and that allows us to solve linear systems. So what we're going to do today here is to interpret the answer for doing just a single elementary transformation as a product of the given matrix with another matrix. And that matrix is going to be this elementary matrix. By looking at sizes, the initial and the new matrix are the same size, of course, so that makes this multiplicand square. And since we're multiplying from the left, it will be of the size equal to the number of rows of the original matrix. So from this desire, from just wanting to have that, we can really immediately get the answer for these elementary matrices. Whatever transformation we do, we can do it, say, with the identity matrix of size m by m, and that is this prime. It's just the result of elementary transformation in question. And that has to be this elementary matrix, because if it works, if this formula works for all matrices A, it should work for the identity matrix, and then the transforming the identity matrix, we will have the product of the identity times the elementary matrix. So that must be it. Just solving this equation. The identity matrix is again the product of elementary times identity. And the identity is such that any product with it is just the other factor. So that's how we are going to find them. But first, let's examine, let's recall three types of elementary transformations and see what happens in each of them. The first, the most used is row addition. And that involves two rows, and I will perform this row addition on the first two rows. But it will work for any pair. So I'll just write elements of these two rows, number 1 and number 2. And I will not care about the rest, because it's not going to change. The row addition, say transforming row 2 with the help of row 1, namely adding a multiple, C multiple of row 1 to row 2, we will have the matrix where the first row will be still the same as in the original one, and the second will be transformed. And that will be the first entry in the second row, and the last will be this. So what we're doing, the rest is still the same. What we're doing is we're taking the first row, taking it out, multiplying by the constant C, and adding it component-wise to the second row. And that is this result of transforming under this row addition transformation. So now we're going to write it as a product, again, of the original matrix. And this elementary matrix. And again, the recipe is take the identity and do this transformation to the identity matrix of the appropriate size, and that will give you the answer. And the identity matrix, before doing transformation, is just ones on the diagonal, zeros everywhere else. And then we are transforming it using this transformation. So we're taking the first row, so zeros everywhere else. We're taking the first row out, scaling it by C, and adding it to the second. In the second row in the identity matrix, we had only one non-zero entry, number 2. The rest are zeros, but when we add the first row to it, scaled by C, we will have C appearing in this position. Zeros everywhere else, as before. So that will be this elementary matrix, and we can check that indeed the product of the two for any matrix A will give us that. And that is simply because when we compute the product, what we do is we can compute the product of two matrices column by column. So each column in the answer we can compute separately by, say, taking the column of the second factor and multiplying by the first. The column number 1, for example, is a vector, a column vector which we can multiply with this matrix, or we can multiply this matrix with that vector rather, and the result will be just that column. So it will be A11 still when we multiply this row of the matrix with the column. When we multiply this row with the column, we'll have that entry, and the rest will be just ones on the diagonal in the matrix, so the corresponding rows will pick just the same elements as we are computing. So that's how we can indeed verify that elementary transformation of row addition type is performed by matrix multiplication. We could continue checking with row swap. So this again involves two rows, and again I will assume that these are the first two rows which I'm swapping. Doesn't matter which pair I'm swapping, but it's easier to write the result when they are number 1 and number 2. And we're just changing their places. So it is 2, 1 rather, sorry, 2, 1 in here as well. We're changing their places. Under this row swap, the rest of the matrix stay the same. And again, we can write it as a result of matrix multiplication, the original matrix multiplied by what is the elementary matrix for the row swap type. Again, the recipe is take the identity matrix, so I'll write it everywhere else up, but not in the first two lines, and then do the transformation, that transformation to the identity matrix. So when we swap the first two lines of the identity matrix, we will have this answer, and then zeros everywhere else. And then will be 0, 0, and then 1 and zeros everywhere else. So that will be the matrix where we'll have block decomposition, if you like, the same as in here. After that, it's just the identity matrix and zeros away from the block diagonals, diagonal blocks rather, and then in the blocks before we had this 2 by 2 in the row swap case. For that elementary matrix, again, we have the block of 2 by 2 with ones away from the diagonal and zeros on the diagonal, and then the rest of the diagonal will be just as an identity matrix, and here we'll have just total 0 blocks. Again, checking that the result is as we want it to be is easy. We can compute it column by column. Doesn't matter which column, the result is going to be the same. So if we multiply this matrix with this column, we do the swap of the entries in the column, just as we want to be, as we want it to be. So that proves that row swap, the swap of rows, is also possible to write, to represent as a product of the matrix which we are transforming and that elementary matrix. So finally, row scaling. it only involves one row. And I will choose it to be the first. And then it involves a non-zero number, C, and the transformation is perhaps the easiest of them all. Just scaling the row as it is in the matrix. So that, again, writing it as a product of the original matrix and the elementary matrix. The elementary matrix has to be the result of transforming the identity matrix with this row scaling transformation. And when we scale the first row of the identity matrix, we will just change the first of the diagonal ones into C. Away from the diagonal, we'll still have zeros. So these are the elementary matrices corresponding to the transformations we did. The code, which allows us to write them quickly and compactly, will be the following. 2, 1 for the position of the non-diagonal entry, and then the entry itself. It's the elementary matrix of row addition. The swap matrix, just telling which rows we're swapping, transposing to 1 or 1, 2, it doesn't matter, it's the same transformation. Here we have a diagonal matrix where all non-zero interesting entries are on the diagonal, and the specific diagonal entry, which is not 1, is in the position 1, and it is C. So these are the codes. In general, we could take a row addition, perform it on any pair of rows, say number I and number J. The corresponding elementary matrix, if we are transforming number I with the help of number J, the corresponding elementary matrix will have ones everywhere on the diagonal and only one non-zero position at the intersection of I and J, and this entry is C. The rest are zeros. So the swap of any two rows, say number I and number J, again will be performed by almost identity, but in I and in J the rows are swapped, so wherever we had 1 we'll have 0, and wherever we'll have 0 we'll have 1. The rest of the identity matrix looks the same. So this is sort of a 2x2 block embedded in the matrix, which is as it was before, but now because two rows I and J don't have to be next to each other, it is spaced out in the matrix. And then finally, scaling number I row in the matrix will be the same as multiplying it with the identity matrix with one diagonal entry changed into C. The off-diagonal entries are all 0. So these are the elementary matrices. And for the row addition, C can be anything, any real number. For the scaling, the scaling coefficient has to be non-zero for the matrix to be what is going to be invertible, called invertible in the next lecture. But in terms of transformations, elementary transformations, it just has to be undoable. So let's quickly look at the properties of these elementary matrices. And the properties will just come automatically from the sheer fact that elementary transformation is a product of elementary matrix and the original one. So if we do row addition twice, if we iterate a row addition with the same pair of rows, transforming, say, row 2 with the help of row 1, first with coefficient C, then with coefficient some other number D. That will correspond to multiplying twice with elementary matrices of the same indices. But yeah, the coefficients we use for this row addition don't have to be the same, could be any pair of numbers. If we iterate such row addition, it's almost obvious if you think about it. Then when you add row j to row I with coefficient c first, and then you do the same, adding row j to the result. So I have to read it backwards rather, because I'm multiplying from the left. That will be multiplied with first, and then I'm adding row j to row I with coefficient d, and I'm continuing by adding the same row j to new row I with coefficient c, and that will be just adding row j to row I with the coefficient c plus d. And that is, again, the property of elementary matrices with respect to matrix multiplication, which can be checked directly, but I'm arguing it on the basis of the relation between row addition and matrix multiplication. The same way for the swap, if we swap twice, it is as if we didn't do anything, so that will have to be in the matrix form. As follows: the product of the matrix of a swap with itself will be the doing nothing identity matrix. And finally, if we scale row I with coefficient c and the same row I with scale with coefficient d, or again the other way around, d first and c second, it will be as if we are scaling it with coefficient which is the product of the two scaling numbers. So these are the three properties which will be useful for us later. The final comment/question for this. Here we were doing elementary transformations on rows and interpreting them as matrix products, because we usually use row transformations, say transforming to a row echelon form, solving a system. What happens with elementary transformations done on columns? The same type of transformations, taking a column out of the matrix, taking it out, multiplying by a number, adding it back. So this will be column addition and so on. So the elementary column transformations are in the very same way can be written as matrix products. But this time, the product will have to be in the opposite order. So the matrix we transform has to be, so this is the result of column transformation on A. It will be possible to write as a product of A and the same type of elementary matrices, but from the right. So that is my prediction. I'm asking you to look into it, to perhaps check it, prove it the same way as it is done here. And that could be used as bonus points for the final exam.